Welcome everyone. Today we're going to talk about some applications of the dot product. In our previous lesson, we learned how to find the dot product of both geometric and Cartesian vectors, and we also ended our lesson off with an example of work. So just as a reminder, work can be calculated by doing the dot product of a displacement vector with a force vector. So what this means is basically we're going to take the magnitude of the displacement times the magnitude of the force and multiply it by the angle between the vectors. So I want you to take a second and see if you can figure out the work done on this desk. Now that you've taken a minute to pause the video, I just want to take a look at a visual of what this would look like. So here we have our desk, and someone is pushing down at an angle of 45 degrees below the horizontal. And this desk is going to be pushed along a horizontal displacement here for 5 meters. Now, typically we want vectors to be arranged tail to tail, so I'm simply going to slide this force vector over so that our displacement and force are arranged tail to tail. So let's erase what we don't need here. So here we can see a little bit more clearly how these two vectors are interacting together, and I'm just going to simply plug them into my work formula. So 5 meters times 50 newtons times the cos of the angle between them, which is 45 degrees. Now, if you don't have a calculator, pause the video and run and grab one so you can work along with us here. You're going to enter this in degree mode, and let's round to the nearest hundredth. You should end up with 176.78 Newton meters. We talked yesterday in our previous lesson on the dot product about how this is also referred to as joules. Now we can see where the Newton meters comes from in the question because our force is 50 newtons and our displacement is 5 meters. So that results in a unit of measurement of Newton meters. Let's dive into a couple more applications of the dot product. The dot product in its geometric formula can actually help us find the angle between two Cartesian vectors. If I simply take this formula above and divide out the magnitude of A times the magnitude of B, then the cos of theta will be isolated on one side. And I can simply do the cos inverse of the products on the right in order to find the angle between the two vectors. So let's box that up. We're going to use that in our examples below. Now, in order to use this, we're going to need to know how to find the dot product between two Cartesian vectors, and we're going to have to remind ourselves how to find the magnitudes of each of these vectors as well. So I'm going to take this piece by piece for this first one. The dot product of two Cartesian vectors is the sum of the product of the x components and the y components. So here you can see we're getting negative 15 plus 8, and that gives us a dot product of negative 7. Remember, the dot product of two Cartesian vectors is always a scalar. And then in order to find the magnitude of a vector, we will do the square root of the x and y components squared and added. So in this case, you're getting root 26 for the magnitude of vector g. And then for vector h, we're going to square each component and add it. And that gives us 64 plus 9. So that's going to give us root 73. Let's enter this into our formula now. Cos of theta is going to equal the dot product between the two vectors times the product of the vectors' magnitudes. Now, I would suggest you leave this in exact form as you're entering into your calculator here. If you'd like, you can combine the two roots on the bottom into a single root before you enter in, if that's easier. And in order to find theta, we're actually going to do the cos inverse of that value. Okay, so try to plug this into your calculator with us here. Let's round once we get to our final answer to the nearest tenth. So you should get 99.2 degrees. Leaving this as an exact value just allows for us to avoid any rounding issues that could potentially impact our final answer here. So for the second example, I'm actually just going to enter this all in together at once. This is going to be a dot b on the top. So I'm going to take each of these x components and add them with the y components. and the magnitude of A times the magnitude of B. Now I'm already noticing here that on the top I'm getting negative 12 plus 12, which is actually going to give me 0. So it really doesn't matter what I get on the bottom. If I have 0 divided by anything, I'm just going to get 0 here. So some of you might already know what the answer of this is without using your calculator, but if you need to, you can use your calculator. You're going to notice that the cos inverse of 0 is 90 degrees. And some of you may be thinking, just based on your knowledge of the cosine function and trigonometry, that there's more answers to this theta. Well, actually, when we do the dot product, if you think back to what we learned yesterday, this is actually talking about an angle that falls from 0 to 180. So within that range, 0 to 180, there's actually only one angle that equals 0, and that would be 90 degrees. Another application of the dot product is vector projections, and that's because vector projections are actually essential to the dot product itself. So we did touch on these in our lesson yesterday when I was introducing the dot product, but we're going to dive into it a little bit deeper today. So I want you guys to think about a vector projection kind of like a shadow. So we're going to imagine these dotted green lines as like sun rays shining down on our diagram. So we're going to see if we can kind of figure out what the projection of A would be onto B in each of these scenarios. So you can kind of see from our diagram here that the projection of A is kind of like the shadow that vector A casts onto vector B. And it's going to be the component of A that goes in the same direction as B. So we can see if our angle is acute between 0 and 90, that our projection of vector A onto vector B is actually going to be in the same direction as vector B. In contrast with that, if our vector is greater than 90 degrees, then we have an obtuse angle, and we can actually see that as the light rays shine down here in our diagram on the right, that the projection is actually resulting in the opposite direction of vector B. And then finally, if A and B meet at a 90-degree angle, we can kind of see as our light rays shine down on vector A, there's actually no shadow that's cast onto vector B. So the projection of A onto B in the case where theta is 90 would actually be 0. And this is also why the dot product of A and B is equal to 0, because there's no component of A that actually goes in the same direction as vector B. So let's take a look at a couple of formulas here. We have formulas for the projections of both geometric and Cartesian vectors, and then we also have formulas for their magnitudes. Now, at first glance, these formulas kind of look a little bit different, but the geometric formula is somewhat buried in the Cartesian formula. So if you rearrange this formula just a little bit here, you're going to notice, based on our initial dot product properties that we went over, that another way to represent B dot B is actually the magnitude of B squared. And another way to represent A dot B in geometric format is the magnitude of A times the magnitude of B times the cos of the angle between the two vectors. And so what happens here is that one of the magnitudes of B cancels out with another magnitude here. And if I just slide this magnitude underneath this vector instead, we actually get the resulting geometric formula that we see up on the left here. So these are the same formula, they're just arranged a little bit differently so that we can kind of utilize the Cartesian properties versus the geometric properties. Usually when we're given Cartesian vectors, we're not given the angle between them, which is why this guy's better for geometric and this guy's better for Cartesian. Another thing that we should know is that when we go into the magnitude formulas here, this guy actually just simply represents one single unit vector in the direction of vector B. Now, if I take vector B and divide it by its magnitude, this is simply direction B with magnitude 1. So in order to find the magnitude of the projection, I actually just eliminate this direction part, and I'm just interested in the magnitude of the vector part. Also, when I talk about the magnitude of a projection, that answer is always positive. So despite the angle being between 0 and 90 or 90 and 180, I always want my answer to be positive. So if your angle happens to be between 90 and 180, we are going to add a negative in front there, and that's going to make sure that our resulting answer for the magnitude is positive. The reason for this is if when I'm talking about a magnitude, I'm talking about the length of that particular vector projection, and I'm not interested in the direction at all. Okay, so similarly, when we find the magnitude piece, I'm basically kind of taking what we did above. So if I backtrack on what we did up here before we canceled out that b, let's say I move one of these magnitudes over. And you know what? I'm actually just going to, in order to show you the magnitude formula here, I'm going to leave a dot b on the top. So really what I'm going to do is I'm just going to move one of these two magnitudes over. And we want to eliminate that piece that is the unit vector piece, which is this piece here, similar to what we did in this geometric formula. So if I eliminate this piece, I'm left with a dot b over the magnitude of b. And these guys here are actually absolute value signs, not magnitude signs. So once I find this result, I actually just want to take the absolute value because the projection, magnitude of a projection should be a positive value. So it's important to differentiate here. I know it's a little bit confusing, but it is important to differentiate here magnitude versus absolute value. Magnitude is actually on the bottom here, so this is the magnitude of vector b, whereas the bars on the outside are representing absolute value. Make it positive. All right, so we're going to take a look at some projections. These are geometric projections here. And it's always important to remember that your sun rays are in the direction perpendicular to the vector being projected on. So here, U is being projected onto V. So I want to imagine my sun rays kind of coming down at a perpendicular angle to vector B, which means that my shadow that's cast is actually going to essentially be, I didn't draw this line very well. It's a little hard on an angle, but it's going to be the piece that goes in the same direction, but also is the component of U that goes in that direction. So using our projection formula from above, let's take a look at it one more time here. If I do the projection of one vector onto the other, I want to take the vector itself times the cos of the angle between them, and then this is simply going to be a unit vector in the direction of the vector being projected on. So in this case, this is going to be equal to the magnitude of vector u times the cos of the angle between them. And this is essentially not going to be calculated over here. So mostly because we can't actually calculate this in geometric format. But there's no need for us to calculate because that in and of itself, if we say it's times the unit vector in the v direction or v hat, we're basically indicating the direction. Okay, so if you have those calculators, let's calculate 5 times the cos of 50. And let's round to about 3 decimal places here. You should get 3.214. And it is important that we write times the unit vector in the direction of v, because this gives us a magnitude and also a direction here. And we know if I'm trying to find a projection vector, I need both magnitude and direction. So essentially this is kind of like a scalar multiple of the unit vector of v. Let's try another one. Determine the projection of P onto Q. So imagine our sun rays are shining down in a perpendicular direction to Q. We're going to end up with a shadow that gets cast in the opposite direction of Q. So this will be your projection of P onto Q. This is again geometric, so I'm going to use that geometric formula that says that I do the magnitude of P times the cos of the angle between them. And this is simply going to be in the direction of the unit vector of Q. So what you're going to get is 20 times the cos of 120 times that unit vector Q, and that's actually going to give us -10. So the negative should make sense because we're going in the opposite direction of vector Q, And we know when we multiply vector q by a negative scalar, it actually reverses its direction. So this should make sense. It gives us a scale for magnitude and also a direction as far as the unit vector for q. Okay, let's take a look at a Cartesian example. Now, if we're determining the projection of vector d, which is this guy, onto vector c, which is this vector here, I want to imagine that my light rays are coming at a perpendicular direction to c. So my light rays are kind of coming from this direction here, and they're shining down, and what I'm getting here is a vector in the direction of c, kind of like this. So imagine that your shadow is getting cast here. So I should expect to get something in the opposite direction of c. So whatever scalar multiple I get, I'm expecting that to be negative. Now, this one's a little bit different because it is Cartesian, so we're going to apply that Cartesian formula. And we're doing d onto c. So that means I'm going to do c dot d over c dot c. Also can be calculated by doing the magnitude of c squared times vector c. So let's plug in what we know. When I do c dot d, I'm doing x components multiplied plus y components multiplied. C dot c is basically the x of c multiplied by itself twice, and then the y of c multiplied by itself twice. And then I'm actually going to multiply it by the Cartesian vector c. So you can see here that this is kind of why we need a different formula for Cartesian versus geometric. So on the top here, I'm getting negative 12 plus 2. That leaves us with negative 10. And on the bottom, I'm getting 16 plus 1. So that will leave us with 17. And then we're actually going to take that scalar multiple and multiply it into each of these components here, reducing if possible. In this case, we can't really reduce, so we're just going to leave it in fraction form. And there's our vector. So we don't really necessarily need a visual for this, but I can simply just apply the same kind of logic that I've just done. We're going to do a dot b over b dot b. Oh, sorry, this is magnitude. So we're going to do magnitude of the projection, and then this is going to be the magnitude of b, and I'm going to take the absolute value of that whole thing. So let's take a look at what we get. So let's do the dot product to start. And then in order to find magnitude, remember we do each of the components added and squared, and we take the square root of that. And if I happen to get a negative here, because I'm talking about a magnitude, we always want to express magnitudes as positive values. So make sure whatever negative or positive you get there, the final answer just becomes positive. So here on the top, we're getting 16 minus 3. That leaves us with 13. And on the bottom, we're getting 16 plus 1. So that leaves us with root 17. And again, this is absolute value. So positive values stay positive. So we're going to actually just express this as 13 root 17. And finally, let's find the projection of A onto B. So here's our vector A. I'm just going to darken that up for us. And here's our vector B. And because B is the vector that's being projected on, I want you to imagine sun rays in a perpendicular direction to vector B, which means that we're going to get a shadow like this onto vector B. So this will be the projection of A onto B. So we're going to do A dot B over B dot B times vector B. So let's enter in what we know. This will be 4 times 4, which we actually already did above, I believe. So these are the same vectors. So I guess we can probably just enter in our answers from above rather than recalculating out this entire thing. Makes a little bit more sense. So that was 13. And then B dot B is simply the magnitude of B squared. So if I already found the magnitude of B to be root 17, I can simply square that, and that will give me B dot B. And this is going to be times vector B, so this will be in the direction of that same vector. And we'll get 13 over 17 times 4 times negative, the vector 4, -1. So let's bring that scalar multiple inside here. We're going to get 42 over 17 and -13 over 17. And there's our solution. Okay, if you need to, you can also do b dot b, and you're going to find that you actually get the same answer of 17 if you're a little bit confused here. But again, b dot b is the magnitude of b squared, and I found the magnitude of b above, which is what I was plugging in there. Okay, last example, we're going to take a look at how we can use the dot product in a sales type question. So our scenario here is that we have a shoe store that sells 300 pairs of Nike shoes and 275 pairs of Adidas in 1 year. Nike shoes sell for $175, whereas Adidas shoes sell for $250. We're going to write a Cartesian vector S to represent the number of pairs of shoes sold. So you can choose X or Y as Nikes or Adidas. I'm going to choose X to represent Nike and Y to represent Adidas. And this is going to be our vector to represent the number of pairs of shoes sold. And then price, if I let X represent Nikes, then I definitely want my X to be the price of a Nike and Y to be my price of a pair of Adidas shoes. Okay, so let's suppose we do S dot P. So S dot P, vector S dotted with vector P, means I multiply the X components and I add the multiple of the Y components. Now look at what I'm actually doing here. I'm multiplying the number of Nikes times the price of a Nike shoe and the number of Adidas times the price of an Adidas shoe. So what you should get out here when you calculate is 130,000. Now what does this represent? If I multiply the number of units sold by the price, I'm actually getting out revenue. So it's actually telling me that the store got or earned $130,000 in revenue. Thanks for tuning in today.